The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome. I'm really excited. This is the second year this class has existed and that I've been teaching it, so hopefully a little bit of the growing pains have been worked out. It should be a fun, good class. So today we're going to talk about a bunch of different stuff. It's all kind of high level, and most of this class is pretty low level detail, and this is high level to give you the macro view before we dive into the more detailed stuff. It's the way I sort of think about it is it's like a toolbox of stuff you'll need every day in this class, either in the back of your mind or the front, depending. So it's sort of just these random bits and pieces, and I apologize, there's no good way to make it be any more cohesive than it is, but hopefully it'll hang together. So we're going to talk about energy in the world generally, review units, review a little bit of EE, do a little bit of estimation practice, which we'll do almost every time we meet, and then just talk about the class and homework and stuff like that. And I forgot my dongle today, so I'm sort of working off of two computers, so I apologize if that gets too crazy. Okay, so if you can grab the document that has a graph on the top left corner, we're going to go through what life is like using a bunch of different development indicators we got from the World Bank in different countries. And the countries I picked are Nicaragua, because that's the country where this class travels to over spring break. And I'll talk more about that later. Haiti, because it's the poorest country in the Western Hemisphere, and so pretty close, and it's been in the news a lot because of some of the tragedies they've had. United Arab Emirates, because this class is also taught at Banzaert Institute of Science and Technology there, and is also a differently very developed nation. The US, because that's where we are. China, because they're also in the news a lot. And then the DR Congo, which deciding who's the poorest country in the world is a kind of impossible task because it depends on what you count, what it is, but DR Congo ranks as one of them. So you can see already there's some pretty severe differences in these different countries in terms of the population, the surface area, and then the resultant population density, which you can imagine is going to have a big impact on the quality of life. So I'll leave it at that, and then we'll draw conclusions at the end. So now we're going to do what I would call a ludicrous quiz, because it's going to be difficult. So the way you do this, and we're going to do together, is first try to guess what the biggest number should be on the y-axis. So what's the largest GNI per capita in US dollars? And throw out some numbers. GNI is the average income a person makes, gross national income. So 30K. Anyone want to say higher? 45K. 45? Can we go higher? Lower? Okay, and what do you think the worst case scenario is? What are the poorest people making? 5? Anyone more optimistic than $5 per year? Okay, and then best guess on who's going to be the one up here. This should be fast, fun. I won't judge you. All right, guess for US. Anyone want to guess someone else? Okay, and poorest? Haiti? Okay, so now, no, that one. All right, so in reality, US, yep, you guys did great with those. 5 is a little low, so by an order of magnitude or 2. And Haiti is the poorest country in the Western Hemisphere, but not in the world. That would be Congo, and so, or one of them. And so, yeah, they're in fact the lowest. All right, so now it's going to get harder. So what percentage of people have improved access to water? This one, we don't have to worry about the y-axis because we're talking about percentages. So we know we're at 100%. So let's take, who do you think has the best water quality access, and what percentage of people have access to clean water in that country? The US, and how much? 99. So basically 100. Anyone want to be a different country or more pessimistic? Okay. A little less than 100? Okay. And then who do you think has the poorest? The Congo? Okay. So let's go check this out. So the UAE actually beats the US in terms of clean water. And we forgot to ask the percent. I forgot to ask the percentage. So oops on that. But I think generally it's higher than people guess. However, these numbers are always complicated in terms of what does that actually mean. Does having access to clean water mean 100% of the time? Are the people collecting the data actually getting good data? Or is there a bit of cheating going on to make your country look better than it is, which happens a lot? So these aren't necessarily things to be confident on. One of the things I find really interesting is that China and Nicaragua are almost at the same level, and Nicaragua is a much, much poorer country on a lot of other measures than China. Okay, next, improved sanitation. So who do you think has the best, and at what level?
Probably UAE again.
UAE, and how much? 90? UAE. Anyone else? This is a class where it's great to participate, and you don't need to be shy about guessing wrong because we're all guessing here. This is not a type of thing you're going to know off the top of your head. Yeah. Improved sanitation. So unimproved sanitation is you poop in a hole, and maybe that hole goes down to the river and pollutes your river. Maybe it's behind your backyard and just sits there. Maybe you don't even have a hole. Maybe you have. So this would be improved to a level that the World Bank considers it actually making a difference in terms of people's health. And if you go to the World Bank website, it explains it more succinctly and more technically than I can.
So it includes like all the services.
Exactly. So, and again, this is for urban access, not for rural access, because in rural areas, you can have a deep hole and that'll work fine if it's dug in the right place. Whereas if you are in an urban environment, there's just too much population density for that to work. So, any other guesses for best case? The US, and how much? 99. Okay, and then what do you think the low bar is? 80%? Oh, you said Haiti? Haiti. Okay, and sorry. And what? And these numbers are all from before the earthquake, so it's worse now in Haiti. And what percentage do you think in Haiti? 50? Okay. So 50, 30, 20, somewhere in there. Okay. So Haiti does indeed win this one, and this was before the earthquake, so it's worse now, as I said. A lot of that has to do with population density, that Haiti is just so dense that it's really hard to manage. There's more people in the urban areas than there are in most other countries. And here, the USA is a little bit better than the UAE in terms of sanitation. There's a sheet that I'll hand out that has all of these, so you can write it down if you want, but you don't have to frantically record everything. Sorry to not warn you of that earlier. Okay, so energy use in kilograms of oil per person. So now you don't get the easy 100. So these are getting harder, as I mentioned. So how many kilograms of oil do you think a person in the US uses per year? 300. Price is Right, high, low, anyone? All right, throw out a number. 1,000. Anyone want to go up an order of magnitude or down? So by that I mean going up to like 10,000 instead of 1,000 or 100,000. When it's this crazy numbers where you don't really have a good sense, it's kind of meaningless to say 300 or 400. All that's meaningful is like 10 or 100 or 1,000 or 100,000. Any other? Are you guys happy with this? Okay. UAE, USA, someone else? China? Anyone else? Okay.
UAE has oil and it doesn't have that many people, so technically.
So they could be using a lot too. So those are all possibilities. All right, on the low end, what do you think the lowest number might be of kilograms of oil? I'm sorry?
Congo.
100? Congo, and how much? 10? Anyone want to go to 1 or 100? Okay. So, there's a lot that we use. Way off. You know, by an order of magnitude, we're at about 10,000 is where we are. Again, these are a few years old, so China's catching up, but it's nowhere near where the US or the UAE is yet. And then Haiti and DR Congo, you guys were low by an order of magnitude. So even in the poorest countries, there's still a decent bit of oil being used for a variety of energy purposes. So with oil and all the other things comes emissions. So what do we think is the emissions? This is getting, again, even harder to guess. Metric tons per capita of carbon dioxide emissions. So how many metric tons do you think you are responsible for each year? Assuming you're the average American. 1,000, 10,000, 100,000, a million, a billion, a trillion, 100,000. I'm sorry? I heard a number.
1,000.
1,000. All right. Anyone want to go above 100K? Okay. And then what about the low? That should be relatively easy because it should scale, right? So if we know that on the previous graph, 10,000 was the high energy and 100 was the low energy, then we should be 2 orders of magnitude smaller, right? So let's see if that works. But that means we'll be between 1K and 1,000 minus 2 zeros is 10. Yeah. So who wants to guess where the high and low is? Where? What countries? China's high. Low? Okay. So Congo is indeed low. It doesn't even register. And metric tons is a big number, so you guys are nice and high on that. We're talking about 10 rather than a zillion. And the UAE, again, is winning over the USA, and China is was not competitive yet. I don't know that they are yet either. Okay, so electric power consumption. Let's do this one fast. So kilowatt hours. Do you guys have any sense of what a kilowatt hour is? Can anyone give a physical example?
Isn't it like the amount of power required to run a light bulb for an hour?
So a kilowatt hour, so thinking about light bulbs is a great approach. So a kilowatt hour, so yes, so definitely how much in an hour. Do you know how many watts a typical light bulb is? 60. So it wouldn't be one light bulb, right? It would be 60 times 10 to get to 600 to get times 2 basically to get to kilowatt hours. So that would be 20 light bulbs in an hour. So how many per person, or is it per person? Yeah. How many order 20, how many sets of 20 light bulbs are we powering each year per person? 1,000? 100,000? And low? 50? Okay, so I'm going to stop worrying about countries because it's getting a little bit repetitive. So in between, you guys were spot on. And here the USA does come ahead of the UAE naturally because the UAE is loaded with oil and we're not. So we do use more coal generally and a little bit of nuclear to fire our plants, but mostly coal. And you can see that in this case, Haiti is very low down, even compared to the Congo, in terms of how much electricity they're using, and you can infer how much electricity there's access to. Mobile cellular subscriptions. So this is no longer getting quite so ridiculous in terms of numbers that we can't imagine. So how many, on the high end, how many mobile prescriptions per person do you think there are? No, so per 100 people. So 80. So this is the population. I assume they go with they don't go to infants. I assume they go to starting with people who might have a cell phone, but I actually don't know that answer. That's a good question.
Maybe a little higher.
Like 90, 100? Okay. And who do you think wins? US, China, anyone else? Wins?
Yes.
Okay. And then on the low end, how many? 30? Anyone want to go lower or higher on the low end? 10, 5. Okay, and who do you think is on the low end? Haiti. Who else? Okay. So this one's pretty interesting. And this is year to year. So in 2008, there were more than 2 cell phone subscriptions per person in the UAE. So they like their phones there. In the US, we're not quite at 100 yet, but we're getting close to everyone having a cell phone on average, and there is that some people have more than one phone issue. But you can see that in every place, there's a pretty strong growth curve, and that's why the cell phone companies are raking in the bucks right now worldwide. Like Haiti going from 1 to 34, that's a pretty phenomenal growth. And everyone, even the Republic of Congo, is doing pretty well, though thinking they were at the top, I'm afraid, is not the case. But certainly the growth rate in developing countries is really high because people are getting cell phones before they get a lot of other more developed devices. And then lastly, internet users. So what's your best guess there? 90? US, UAE?
Does this include accessing the internet on your phone?
I don't know. I think this study was probably done before that was quite as prevalent, because even like in 2008, you were using your phone for internet access a whole lot yet less than you're doing in 2011. But let's say, I actually don't know, so I can't even say let's say something. But yeah, I'm not grading you on this, so it doesn't really matter. It's just to give a sense. So what, 90, does anyone want to take a different? And then on the low end? 21? Okay. So here you can see that we're pretty far behind in terms of internet versus cell phones, which isn't all that surprising. So the US is lower, the UAE is a whole lot lower, and in the developing countries like Republic of Congo, you might remember, I think they were at 14 people had cell phones per 100, and they're at half a person per 100. So internet access is a whole lot lower, and you can think about the reasons for that, and they probably make sense why it's harder to get internet access than cell phone access in a developing country. So that was our ridiculous quiz. What might you take away from those trying to guess those ridiculous things? You need more DLAB classes. Absolutely, I'll support that. What else? Yeah.
The developed countries really contribute to global emissions.
Yeah, developed countries absolutely do. I don't think that'll come as a shocker to anyone who's read the newspaper in the past 5 years. But yeah, but it's helpful to see the actual numbers as opposed to just a gut sense, totally. What else?
Technologies, like if you have cell phones in a range, there's a possibility you can bring something else and you'll sort of embrace it and use it within a few years.
Yeah, so a technology that actually really works for people is going to be embraced, absolutely. And one like an internet workstation, or may not be one that is embraced because it's impossible to embrace. So that's a good takeaway too. One thing I take away from this is that there's not much gut instinct here for me either. That we talk about, metric tons of carbon dioxide emissions. We talk about all these different things in the news, but do we actually, as MIT scientists and engineers who are some of the brightest people in the world on these sorts of topics, know these details? Heck no. So when you're starting to think about what it means to do this work in a developing country, making assumptions like how many cell phone users there are or how many internet users there are or any other detail about life is a pretty dangerous thing to make an assumption on, and you have to get the data in order to do good work. There are some trends with poverty that we can take away. So you did see like Nicaragua, the Congo and Haiti were always on the lower end compared to the more developed countries we're looking at, but Haiti, Nicaragua, and Congo all took turns who was the lowest. And so even though you can very distinctly say who is making the least per income per capita, that doesn't necessarily translate to who has the fewest cell phone subscribers or something like that. And the last thing is when you watch, yeah, do you have a question?
You can continue, but I was just going to say that the takeaway was the opportunity that like these countries are developing, though. And so when we're enabling them to technology, and while they're developing, it'd be great if they never developed the greenhouse gas emissions.
That sure would be, and that's one of the challenges for doing this type of work is everyone pretty much wants hypothetically to lead a life where everyone has a car and everyone has air conditioning running or heat running 24/7 like we do. And if we try to create our environment worldwide, we're not going to have a world for very long. One other takeaway I have is that you can get an assumption if you've never traveled to developing countries when you see the photos of charity for commercials and stuff like that of how hard life is, that you can assume that life is completely dire and that 0% of people have access to clean water, 0% have access to electricity, no one has a cell phone, and that's not true either. And so you neither want to assume that everyone has this, but you don't want to assume that life is impossible and everyone's living, in sort of the Dilbert mud universe where all you have is mud and that's it, which is easy to happen if you've never traveled and all you see are like Save the Children ads on TV. Not to bash Save the Children, but their ads are pretty stark. This is tough. Okay, one other way to think about development is just to look at the world at night, which NASA does by compiling a bunch of photos of pictures at night. And so you can very quickly see where lights are and where the wealth is. The drawback being that fire also creates light, and so areas where there are big fires will also look like they're well developed. And so that's often the case that in Africa there's fires burning out of control, and that's why it looks like it's developed. But just like a kitchen fire is not going to show up on a NASA graph. But it's an easy way to sort of think about where are population centers in developed countries, and then also where is enough money to have electricity to have lights. So you can see things like India is actually pretty lit. And that plays out in terms of how India is doing. It's really been skyrocketing in terms of its development. And so there's a lot more electricity there than there was, though there's certainly plenty of work to be done in that country to make life easier. Was there a question? Yeah.
I was just going to say, there's a map sort of like that which connects like Facebook connections, and it kind of looks the same. And somehow you have like this, you know, like even China right now is pretty dark, which is quite surprising because you expect China to be quite developed.
Yeah.
And same with Facebook actually.
Yeah. Well, and it's kind of fascinating. I think in every developing country, there's not an even distribution of wealth. Just like in this country, you've got your Bill Gates and Warren Buffetts, and you have people who are starving to death in this country. You have that true in every country. In Haiti, you can see mansions and you can see hovels, and you can see that everywhere. And so there's always going to be that uneven distribution wherever you go. So Nicaragua, why did I pick Nicaragua as the place to travel? Well, it's a pretty great place in terms of renewable energy sources. So you can see that it has a lot of different sources. It has wind on the coast. It has a bunch of volcanoes which provide geothermal energy that they're taking advantage of. Rivers that can provide hydropower, solar energy because it's basically on the equator. And they grow sugarcane, so you can grow ethanol. So it's this really nice place in terms of lots of opportunity as compared to some other countries where there's fewer natural resources. And so if you want to start in a country, it's nice to start in one where you have something to start with. But Nicaragua is the second poorest country in the Western Hemisphere behind Haiti. And yes, Haiti is well behind Nicaragua and more so after the earthquake, but Nicaragua still has a lot of need. I forget exactly when, but about 10 or 15 years ago, Nicaragua was about 70% renewable energy. And as people's desire for energy has gone up and the cost of oil has stabilized, they've actually sunk back down to about 30% renewable energy, which is a sad thing, especially considering that Costa Rica, I think, is about 90 or 95% renewable energy. So it can be done. Costa Rica is a next door neighbor to Nicaragua. But their goal is by 2013, which is getting ever closer, they want to be at 3% oil, which is pretty ambitious given that they're at about 70% right now. So there's also, but that translates to there's a lot of interest in Nicaragua to use renewables. So that makes doing work in that country easier as well. They're also close by because we're traveling over spring break, and that's a very fast trip. The idea of flying all the way to Africa and spending half your time in the air and spending all of your budget on the airplane tickets is not a great idea. So that's the other reason Nicaragua is of interest. Okay, so let's talk a little bit about energy. So we talked a little bit about how much energy is used worldwide. So let's talk about where it's coming from. And you can see that coal and oil really dominate where our energy is coming from. And all these renewable energies that we talk about are pretty microscopic. So the world has a long way to go before we can actually reduce our greenhouse gas emissions and things like that. There's a really big problem with this slide. Does anyone see it? So email me if you find it. I'll give you extra credit. Say again? It does add up. Okay, so, and now exergy, and for the purposes of right now, you can consider exergy and energy to be basically the same thing in your head. That's a total lie. And if you know anything about exergy, you know I'm lying to you, but it's not that critical to think about the difference. And so you can see, where are we spending our energy? And it's actually pretty well distributed between all the different needs. Not entirely, other is carefully constructed to be about the same size, but what this means is we can't just somehow magically replace all the cars in the world and solve all our energy problems, or somehow magically stop needing agriculture and have no more greenhouse gas emission problems. There's a lot of issues worldwide that need to be addressed, and they all need to be taken into account. Okay, so, and why is it so hard to switch? Well, the energy density of what we're used to using, so diesel and gasoline and such, are awesome compared to batteries, flywheels, compressed air, some of the things that we talk about as being the great alternatives. And so going from something that's an order of magnitude worse and it's harder to come by is not an easy sell because it means it's going to be a whole lot more expensive and less pleasant to use. So that's why this is such a difficult problem. But because we're running out of those really awesome ones, we're going to have to figure it out. Okay, so units check-in. So one of your sheets says units check-in on it. And so if you can pair up, preferably with someone you don't know, and go through the units. Again, I'm not going to grade you on this, but I would like to have you turn it in with your name so I know who, where the class stands overall on this knowledge. And you guys can work in teams and just turn one sheet in. This is an area where, let me grab one, where hypothetically we should all know every answer as MIT members of the MIT community. I know there's a couple of people from Harvard, so maybe you get a pass, but because you're not necessarily an engineer or scientist. I wasn't trying to slam Harvard. But these are actually things that there's a few in here that are a little subtle, like inductance, that you're not going to need to know. That was just to check how everyone's doing. But most of them, torque, work, power, energy, pressure, resistance, those you should know. Are you out? So those are things that are all really useful to know for the rest of your life. It's really handy to know how energy and power relate, what is energy, what is power, and something that most people don't know, including engineers and scientists, and is an embarrassment to our educational system that most of us don't. So I hope that through this class you will be forced to get it into your brain for long enough that it'll stick. So yeah, definitely learn that stuff. All right, so what is energy? Anyone? You've got your units in front of you, maybe that'll help. Measure potential work. So then what's the difference between work and energy? So energy is the ability to do work. Anyone else? The measure of potential work, did you say? Okay. And then what's work then? I can't hear you back there, sorry.
Force over distance.
Force over distance. Okay, can you give me something that's a little more intuitive? Because I don't have a great intuition of force over distance, though kind of I do. I think I could work that out.
If you want to use the energy, you're required to put objects over a distance.
Yep, okay. So the thing that confuses me about that is you said work is force over distance, and then you said it's the energy to move an object over a given distance. So then I would think the equation should be E over D, not F over D.
So it's force applied over a distance, like it's a force into
Not over a
distance, not over its own.
Okay, so force over a distance. Okay, cool. Any other definitions? Okay, so the way that Saul Griffith likes to think about it, and I took these slides from him, he's an MIT alum who does a lot of work in energy realms as well as design and other great stuff, is it's thinking about lifting an apple from the ground to a table. So does anyone know how much an apple weighs? A newton? Yeah, that's a really good guess. Does anyone know how much a newton is? So, well, so a kilogram and a newton relate. How do they relate?
1 kilogram per meter.
Yeah, so we're just talking about mass versus weight, right? So mass is disregarding gravity and weight is regarding gravity. And so a newton is taking into account gravity. But yeah, an apple is about half a pound, which is about a newton. So I have 2 apples here, so you can get a physical intuition for that because so just pass them around. Physical intuition is really, really handy. And I know the lengths of my thumb so that I know how long an inch is and how long 7 inches is, and hopefully have some sense of weights and distances too. So that's why it's really nice to have an equivalent. And you can even take that apple and feel what it physically feels like to lift that apple from the ground to a table. And because a table is about a meter, so we're talking about a Newton meter, which is your joule. So then, what is power?
Energy per given time.
Yeah, exactly. So we could think about how many the watts associated with moving a bunch of apples from the ground to a table. So moving 40 apples from the ground to a table is 40 watts, which is the power associated with a light bulb. And so light bulbs are using a good bit of work if you think about how much work it takes to move 40 apples from the ground to the table. You can do it, but you wouldn't want to do it all day, every day, for as long as your lights are on.
Also per second.
Right, for second, yeah. So you're doing that every second if you're powering your light bulb, hypothetically. So does that make sense to everyone? If this is a good analogy for you, awesome, use it, keep it in your head. If it's a terrible analogy for you, which it probably is for some of you, get creative and think about what might be a good analogy for you. You can Google on the web. There's lots of different people who explain this in lots of different ways. But these are 2 concepts that is really good to have in your mind. The other one that I like to do, which is a little obscure in some respects, but really helps me, is to recall that power is analogous to a velocity, and energy is analogous to a distance. So that's another way to think of it in addition to the apple analogy. And however you're thinking about it, so running that apple out, I don't know what this HP or IBM takes, but it takes about 60 watts. So it's moving 60 of those apples every second for as long as I keep it on. The other way to think about, in addition to apples, is light bulbs, because again, we have light bulbs as a quantity that we kind of know, and we know that, powering a light bulb is a whole lot easier than powering a toaster oven or a space heater. So you can kind of think in those terms. So when someone says something is, a kilowatt generator, you can think of what we did before. You can think about how many light bulbs in a kilowatt. Yeah.
So when a light bulb is energy efficient, it's really more power efficient.
Yeah. So energy and power the difference is whether you're thinking about time or not. So energy, if you think about it in terms of distance, I can say that I walked a mile today, and you can say, great. And if I did it in 4 minutes, you can say, wow. And if I did it in 4 hours, you can say, unimpressive, right? And so energy is just telling you that the equivalent of how many miles you walked, and power is telling you how quickly you did it. Both are really important. So a light bulb that's 40 watts is telling you how much energy is going to be required in a given amount of time to turn it on, to keep it on. So it's confusing. I promise you I will screw up and say the wrong word occasionally, and if you do and you catch me, I really appreciate it. So, all right, so let's do, are there any questions about all of this? It's hard to think about. I've been in grad classes where students screw it up royally, so don't be saddened if you do, but it is really important to get a good intuition on it in any energy class, and hopefully as every engineer or scientist will have one by the end of their career here. Any other questions? Okay. So hopefully this equation looks familiar to everyone. Is there anyone who doesn't? I know this is awful to ask, but is there anyone who this doesn't look familiar to? Because this deals with something that is an assignment that's due tomorrow. So if it doesn't look familiar, I need to give you a different assignment because it's not fair. So if it doesn't look familiar and you don't want to embarrass yourself right now, or not embarrass yourself, but be open about it, let me know after class. So what's the V? What's voltage? I couldn't hear all of that. So voltage is what? Is joules per coulomb? Anything else? Yeah, the difference in potential. I apologize about my handwriting. And can you think of the analogy, the classic analogy for voltage? You said water pipe stuff, yep. So what's voltage?
The height.
Yeah, so the height, the water pressure. All right, how about I? Current, yep. And current is amps. Amps, the flow. Yeah, and that analogy is easy. You can think of it as the flow. And then what's R? And so that would be the ohms. Yep, go ahead. Yeah, so the pipe, exit diameter, etc. Yeah. So this is a handy equation to know. We don't have to do too much double E in this class, but you definitely have to do. Electricity always bugged me because it's invisible, and as a mechanical engineer, I don't really enjoy thinking about things that are invisible. So I think it's tough, and yeah, I like the flow rate analogy a lot, thinking about the pressure and the water flow and the resistance to that flow. That helps me a lot. So why am I reviewing this to you? What is useful about these quantities? So in this class, one is we can predict battery life. So batteries are measured in amp hours. So how much flow over how much time. So you can know how long your battery is going to last, which is really important when you're, say, sizing a solar system, a solar panel system, or something like that. Secondly, not destroying LEDs. So I'm about to give you an LED and a battery and ask you to figure out what size resistor you need to connect the two, and then do a couple other things. So let's review how to calculate that really quickly. Can anyone walk me through it? So the battery is a 9-volt.
Do we know how much current the LED makes?
Yep, so the LED is a 20 milliamp hour LED. What else do you need to know?
How long is it?
Yeah, so how long you're powering it might be important. In this case, it's a flashlight, so it's something you're going to turn on and off, and you can probably estimate how long you're going to need it. The voltage you're absolutely going to need, so it's a 3.6 volt LED. Does anyone know what LED stands for? And does anyone know what a diode is? Go ahead.
It's essentially a kind of a one-way pathway
Yeah.
So essentially it's a one-way gate.
Yeah, so it's absolutely a one-way gate, and the light-emitted diodes happen to emit light when the current passes through, which is really handy. So the one-way thing is really important to remember. When you're connecting everything, if it's not working, that's a hint. You'll notice that I drew this LED with one leg longer than the other. That's because that's how they come, and that's a hint as to what direction you should put them. So you can do that by trial and error, but once you figure it out, then you can write down the longer leg, what direction that needs to go in. So we know that our battery is a 9-volt battery. Awesome. We know that our LED requires 20 milliamp hours and 3.6 volts. And we know we've got this equation, and I told you that you need a resistor. So we're probably looking at what we want the resistor to be. So what do we do from here? Yeah.
So you know that you have the remaining voltage that you need to drop before the circuit sort of finishes off. So you need to drop off that much V in your resistor, and you know what the current is because it's 20 milliamps. So divide it.
Yeah, exactly. Are there any questions? So, okay, cool. So I'll explain the assignment, but that's going to be very useful. All right, so that would be another reason why you need to use that information is if you don't use a resistor, you're going to blow your LED, and you only get one, so you don't want to blow it. Power is equal to the voltage times the current. That's another useful one. Does this look like any other equation you might have seen in a mechanics, more oriented mechanics, what power is equal to? Power, I squared R, is that what you said?
I mean, VIT would be heat, right? Like power into time would be heat. So VI just reminded me of the heat equation, I square R.
Yeah, absolutely. So, and it does indeed equal I square R. So, but in terms of mechanical, power and work are
Just over time.
is it over the time? Yeah, exactly. So I had to remind myself. So I just froze. But yeah, so the so power is, what's another way of thinking about power? Work over time. Yep. And what's work? Say again? Yep. So, and what's a joule? Say again? A Newton meter? Say again?
Over time.
Exactly, over time. So, excuse me?
Force velocity.
Yeah, exactly. So, however you get to it, power is equal to force times velocity. And so, which it's annoying because we only have so many letters in the English language to work with. That this velocity is different from that voltage. But you can sort of think of the voltage as a force, like pressure, and the I, like a current, is sort of like a velocity. And so that's how to get back to relating the mechanical side of things to the electronic side of things. And something they never told me until I got to grad school is all these equations you use in electrical engineering and all the equations you use in mechanical engineering are all based on the same formulas when you go back far enough in the physics. And so we're all just talking about the same stuff. We're just using different assumptions and different variables. So if you're more comfortable in the mechanical world, figure out what it is in electrical world and do the translation in your mind, or vice versa. It's a nice trick. If these are totally unfamiliar concepts, these are 2 books that I posted on Stellar that I would recommend grabbing out of the library to be a refresher, starting with the Schertz book. So a lot of this class we're going to do estimation because it's a really handy tool for doing work in developing countries and as engineers and everywhere. So we're going to start with how to estimate the energy in that 9-volt battery that I'm about to give you, that we just talked about. So Here's the 9-volt battery. And how do we estimate the energy stored in it?
That's how long it would power like a flashlight.
Yeah, how long to power something like a flashlight? So let's go down that path. So what do we need to think about in order to figure out? So the reason I put that underscore there is just because you could think about how long it takes to power something else if you know that better than a flashlight. But yeah, this is a really good way to think about that. So what do we need to think about in order to know that? So how long does a 9-volt battery power your flashlight for?
You need to know how much power the flashlight consumes, like a rough number for that.
Yeah, so how could we get a rough number for that?
Should be less than a light bulb, so it's smaller.
Okay, but it's still a light bulb.
The light bulb
Yep.
is not like a big bulb.
So a small light bulb. So we are powering a little light bulb. So what do you think that light bulb might be rated at? 20 watts? Anyone else have a different thought? 10? All right, so generally in estimation, you go with orders of magnitude like we were talking about before. So if you know specifically that you're using a 20-watt light bulb, put that 2 in. But if you don't, just go with 10 or 1 or 100. And then hopefully the small digits will cancel each other out. But in estimations, we're never trying, at this level, we're never trying to get to an actual exact number that you're going to use in a specific equation that you're going to use to actually design a flashlight. You're just trying to get an order of magnitude. Can I power a flashlight, or can I power this light bulb with a 9-volt battery, or do I need a bigger battery type of thing? So let's go with 10 watts. So we know the flashlight, or the light bulb is 10. We think the flashlight light bulb is 10 watts. What's next? Someone else. No, you're doing great. Yeah.
Just calculate the amount of time it takes.
Okay, yeah. So let's multiply it by time, and then what will we have?
Energy, if you multiply it.
Yeah, we'll have our energy. Awesome. So how long does your flashlight last? $10 hours? So what happens if I do this? What's wrong? Yeah, my units are totally off. So 10 hours, so what units do I want? Yeah, so 60 minutes per hour times 60 seconds per minute is 3,600 times 10 times 10. So what are my units now? Joules, yeah. Awesome. So does that sound good? So 36 kilojoules. When I did this, the way I did it is I've never had a flashlight that uses a 9-volt battery. I only have flashlights that run on D cells or AA cells or whatever. So I didn't really have a good sense of how long my light bulb would last on 10 hours. And so I estimated that, well, first I thought about how a battery works. And how does a battery work in really simple 15 or 10-year-old terms? Yeah, so there's a chemical reaction which requires chemicals which are volume based, right? Like you can sort of change the layering of the different plates that you need in a battery, but fundamentally you can only have so many chemicals in a battery. So I thought about it like 2 AA's is about the same volume and set as equivalent. And then therefore I said, all right, well my flashlights, I forget how long I thought they lasted. I thought my bulb was actually 5 watts, so I cheated and put a 5 in there instead of a 10 or a 1. And I thought it lasted just an hour. So I got this many joules, which I believe is actually closer to how long a 9-volt will last, depending on how good your 9-volt is. So you can see, but we're still you guys are still in the same order of magnitude, so we're golden. It doesn't really matter, but just to give you a slightly different approach. So now let's talk about estimation. So why am I bugging you to do this in an energy class? So one is that it's really handy when you're in a meeting, say with a community partner, and a community partner says, I want you to install me a solar panel, and my roof is this big, and I want it to power all the ovens for my kitchen. You might be able to very quickly, rather than saying, I don't know, or that sounds stupid, you might be able to very quickly do the equations to say, actually, you'd need a solar panel the size of a football field to make that work. So let's think of a different method. It's a really good way to gut check your work or your other people's work. So if you read in a newspaper that someone's come up with a new magic energy source that does this amazing stuff, you can really quickly check and see, does this make any sense, or is the reporter not doing due diligence? Or when you come up with an answer on a homework set or a design problem, find it out. And then also saving time and money, that you don't have to spend the time to figure out spec that whole solar system that community partner wanted before you've actually figured out, is the solar panel going to work at all for you. Estimation tends to feel really hard, and that's really legitimate. So there's a lot of reasons that that's the case. One is that you're used to problem sets where there's generally a right answer, and exams where there's generally a right answer. Certainly that was true in high school, and often is true even at MIT. And in estimation, there's kind of a right answer, but there's a lot of different assumptions you can make that could give you a lot of different right answers. You're also used to defined realms, where you know you're going to be given a test, and it's going to test you on these 10 equations and how to use them in these 5 realms. And that's all you need to know. And this is out of that comfort zone and totally in a different space. You typically have no resources beyond your brain. So yes, we have Google. You can always use that. But in this class, we're often going to be doing it with no Google. And so all you have is your brain. And so it's nice to be able to lean on a textbook or Google or whatever. It's often in public. So there's little time, there's little warning. That can be terrifying. You'll see me screw up. You may screw up. It's hard. But it's really worthwhile, as I talked before. Again, it's open-ended. It's ill-defined. There's multiple acceptable methods and answers. The significant uncertainty, is a light bulb actually 5 watts or 10 watts or 1 watt or bigger? It's hard to know exactly if you can't actually look at the light bulb. And that can be stressful. And then you have to have this set of knowledge that you don't just know values or quantities or relationships, but you know all of them in relation to each other. And that is a lot of knowledge. So that's one of the reasons that I'm trying to push you to have these units at your fingertips, as well as having some quantities like how much is an apple, things like that, so that you're going to be better at estimation, because part of it is practice, and practice is huge, and we're going to be doing that a ton, and the only way to get decent at it is to practice. But part of it is having those quantities in your head already, so that some of that uncertainty disappears. So what are the actions that you can take to do effective estimation? So identifying a problem system. So that generally involves drawing these pictures. So I drew my battery, and I know it needs to power a light bulb, and I know they're connected. And that is a good way just to think about it. Drawing your system always seems to help in problem solving. Identifying a quantity within a system. So in this case, we identified that there's a battery and it's 9 volts, and we identified a 10 watt or 5 watt light bulb. Providing a value for the quantity, so I kind of combined those two, right? But you could think, all right, I need to know the voltage for this, I need to know the wattage for that, and then think about what it is. And then also with time, we really did that. We thought about time, and then we figured out what it needed to be. Counting a set of things. So I'm trying to think of a good example for counting a set of things. So for example, like if you're estimating how many seats there are in 10 to 50, you could count a row and then multiply, right? So, or if you're estimating how many light bulbs in a kilowatt, you count one and then you multiply. Comparing two systems for a quantity. So I compared my AA's to a 9 volt because I'm more comfortable thinking in AA's than I am in 9 volts. Every time you do that, you're making another assumption. It's a little risky, but it's better than doing nothing by far. Identifying a relationship between quantities. So we did that. Power times rate is the energy. And then we have changing a system scope. So that's what I did, getting from 9 volts to AA's. And identifying a similar system. I guess scope could also be, or a similar system could be thinking about this chemically. Like you could skip all these energy equations, and if you were a chemist and really comfortable with chemistry, you could just figure out the chemical reaction and do it that way. I'm not a chemist, so that's not the way I'm going to pick, but it would be another approach. And then, as I mentioned, practice. Okay, so now we're going to do a harder estimation together, and then we're going to take a break. Because I know 3 hours is an incredibly long time to sit on uncomfortable chairs in a poorly laid out classroom. So how do you want to approach this bicycle problem? I'm sorry? Oh, yeah. So this is estimate the drag force on a bicycle and rider traveling at 20 miles per hour. And I gave you a little help. That's 9 meters per second.
By drag, do you mean like the wind as well as the ground?
So what do you think is bigger?
Ground.
You think the ground is bigger?
It's traveling at 9 meters per second.
Does anyone have a different approach? So I think the wind is going to dominate, and so you could include the wheel friction, but in an estimation, you want to just look at your biggest quantities. So I'm going to say we can neglect that friction and just focus on the drag associated with that body going against the wind. And this is the question last year. This is just a silly looking bicycle. That's why I posted it, because I find it amazing. But we don't need to worry about whether the person is facing the wind this way or this way. We can assume the body, you can neglect that, worrying about that. So what do we need to think about?
Surface area could be basically.
Yeah, so we can think about the surface area. So how do you want to model our person? All right, so triangle, we could do a triangle, we could do a rectangle. The equation for area of a rectangle is a little bit easier than a triangle because you don't have to divide by 2. So let's go with rectangle because it's kind of meaningless. So what's the area of an average person? Half a meter squared. Okay, great. So we have our surface area. Does anyone know how surface area relates to drag force? So the drag force is equal to a drag coefficient times the area. Say again. Times velocity. Does anyone know that drag coefficient? This might not be the best approach. All right, so this was step 1. Didn't work. Or it's one that we could go after, but you're trying to answer this question right now in the classroom without looking up that drag coefficient. And we don't have any people who've been spending too much time on fluid mechanics, so we're going to have to go a different approach, which is great. So what would be a different approach?
Density, the density varies. So kilograms per meter cube. So if you know how many, the volumetric flow that's impacting the person.
So we have kilograms per meter cubes. So you're saying to multiply it by area to get kilograms from... I'm sorry?
velocity there to get the volumetric flow.
Mm-hmm. So I think we're actually here still. So now we're getting an equation that actually has the right units, so that's great. But because we've added in the density, and we could say that this is just a constant, and we're doing an estimation, and so we can neglect it. So absolutely, this would be one way. So let's work it out. So does anyone know the density of air? Is basically 1. Yep. So, and then we have our area is 1/2, and velocity is 9. So that's basically 5. 5 what? Forces in. Yeah. So 5 newtons. So how can you gut check if 5 newtons sounds like a good number? Okay, so what is a newton? An apple. All right, so we're talking about the weight of 5 apples. When you ride on a bike at 20 miles an hour, is that fast or slow on a bike? It's pretty decent, yeah. So how many people have ridden a bike before? All right, awesome. So we're getting into familiar territory. Great. So when you're riding on a bike, does it feel like it could be 5 newtons on your body? 5 apples? Okay, so if I said, could it be 500 apples? That's ridiculous. If I said like 0 apples, you'd probably say no. You're feeling something against your body. So maybe we're in the right realm. Cool. Great, so good job. A lot of people give up on this approach because you can't remember that constant or whatever, or you're missing a term in this one because we need that row in there. But this one worked. The way I do it, the way I approached it, is I thought about the power associated with bike riding. So when I bike at the Z Center, it tells me actually how much work I'm doing, how much power I'm generating. And so I'm kind of a terrible biker. You can tell I'm a little out of shape. But I know that I can bike at somewhere on the order of 200 watts. And so that means I'm all set, right? Because now I have that, and now I just need my 9 meters per second. And what am I doing wrong? That's what I'm doing wrong. I need to divide. And so then I get about 20 newtons. Is that right? Did I do that math right? Sorry, board fatigue. What?
Yeah, that's about right.
Thank you. Yeah, I know I'm not actually dividing 9. I'm dividing 10 because with estimation it doesn't matter. So we're kind of in the same order of magnitude. We're a little different. But this is a nice approach because it's just 2 quantities, and all you really have to think about is 1. And you can this 200 watts is actually ambitious for biking for a long period. That's a lot of power you're outputting. So because you can see it, you actually see it on the screen. And some people who are really into biking know like Lance Armstrong can do and what a normal person can do. Yeah, but so this is just a nice way to see there's 2 different approaches to this problem, and I'm sure there's others that you could go after too. So there's always another way. Estimate how high a D-cell can lift you, and if you have a background that's not engineering based, if you can find someone who is, that might be good to have the mix rather than 2 non-engineers working together on this. Though you guys may do fine too, so it's worth a shot. So yeah, so take 10 minutes to work on that problem. Okay, does every team have a guess? Does any team not have a guess? Or can you raise your hand if you have a guess? Okay, great. So did anyone have 1,000th of a meter or 100th of a meter? 10th? A meter? 10 meters? So maybe 16, 100 meters for 1,000, 10,000. Okay, so we're pretty constrained. How do these numbers strike you? Is reasonable, ridiculous? Okay, so, but there's an aspect to this that's ridiculous, period. The question is a little funny, right? We can talk about that. So, can someone go through how they got 10, order of 10? Yeah.
So basically what we did was we did the same thing that you did earlier. We thought about how long a D cell could power a 10 watt bulb. And,
Okay, so you have your D cell system.
Right.
How long, or let's do time till it lasts for a
Right.
10 watt bulb?
Right.
Okay.
And we came up with we came up with a number that when we solved, we got 15,000 joules as the energy.
Mm-hmm.
And then basically like we equated it with the potential energy of a person weighing roughly 50 kilograms at a height x.
Yep.
So that would be mgh. That would be 50 into 10 into x.
Mm-hmm.
And that would be equated to 15,000.
Yep.
And then you solve for x,
Yep.
and x turns out to be 30.
Okay. Did anyone take a different approach? I kind of led you guys down to this approach given the previous exercises, so I'm not shocked that no one did. For the people who got closer to 100, what was the assumption that was different that led you to 100 rather than order of magnitude 10? Yeah.
Our battery, we put in that it had 180,000 joules. Not
180,000 joules?
Yeah.
And where did that number come from?
10 watts for 5 hours.
So you guessed 10 watts times 5 hours got you there. So it was really just, because I think you guys had 10 watts too, so it's just how long does it last? 15,000 joules is about what the 9 volt lasted for. And how does the volume of a D cell compare to a 9 volt? So I would say a D cell is actually maybe 50% bigger. So I think 180,000 might be impressive, but 15,000 is a little low. But we're all pretty close to the same ballpark. And I actually think that we're closer to 100 than 10, depending on the assumptions you make. So, but everyone did great with these results. So why isn't there an awesome person lifter powered by a D cell out there so we can all get to the top of our roofs to shovel them off or whatever you need to do? You probably not shoveling your dorm roofs, but I sure need to shovel my roof if I could get up there. So, efficiency, yep.
It's also instantaneous, right? You're assuming that the battery like lifts you up and that's it. So it would be like.
Well, not necessarily. Like I didn't say how much time it took. So, yeah. So there are some efficiency issues, but this exercise was actually run in a class called 2009, which is the senior mechanical engineering design class, and a guy called Nate Ball came up. Oh, I'm clicking on the wrong computer. With what he calls the Atlas powered rope ascender that basically does this. Of course, there are some efficiency losses, so it's not actually a D cell, it's a much better battery, but it's in the kind of the same ballpark. And so it's kind of amazing because you wouldn't think that a D cell would have a chance of lifting you anything, right? But the embodied energy in a D cell is actually pretty good. And at the same time I'm telling you that, I also showed you that graph where I told you a battery is lousy compared to gasoline. So it's good in some respects, but it's also lousy if you actually wanted to, say, power an automobile with a D cell versus a person lifting up a little bit. An automobile requires a whole lot more energy to work. Okay. So finally, after all this other stuff, we can talk about the class now. Now you have a sense of what the class is going to be like. So I'm Amy Banzaert. I have a 3-year-old. His name is Eli. I do work in developing countries, mostly on charcoal, which you'll hear about later. Our TA is Amit Gandhi. Where are you there? Where?
Brazil. I went to Brazil for IAP's term.
I don't know how to share this.
Yeah, so I went to Brazil, and I've done work in Ghana, Guatemala, and Brazil before.
We have a bunch of other staff who are helping. Dennis Nagel works downstairs. He's the shop manager for D-Lab. Steve Banzaert, who you may notice the last name is disturbingly similar, is in fact my husband. And he's also really good at double E stuff, so we helped teams last year and he'll do that again. Ken McGaney is a mechanical engineering grad student. Sarah Reed just finished her master's here in Mechie, is really good in design work. And then Amelia Servey, also a mechanical engineer. Because of the design class, we're kind of slanted toward mechanical engineering support. And then we'll probably add a few other mentors along the way. So our syllabus, so if you guys want to break out your syllabus, you now know who's going to help everyone. You can read the aims and the objectives, which I have worked pretty hard to make sure that everything we're doing aligns with those aims and objectives. So that should give you a good sense of what you can hope to come out of the class with. And if those don't align with what your hopes are for the class, maybe this isn't the right class for you. And if they do, awesome. I'm glad to have you. So this is a 12-unit class, which means hypothetically you're spending 6 hours a week in class and 6 hours a week out of class working on all the activities associated with the class. And last year was a 9-unit class, and students said it was very much 9 units, and they said there was not nearly enough time to do everything they wanted to do in the class, which is why we bumped it up to 12 units. So I think it is reasonable to expect you'll be spending 6 hours a week out of class, and this is a class where attendance is expected. So I know there's a lot of classes at MIT where you can skip the lectures and the labs, or at least the lectures, and do okay. And this class, like those estimation exercises, you can't really capture what we did in the lecture notes, and so you'll miss the learning entirely if you don't show up. So there is sort of a strong punishment in terms of grades if you don't show up to class without a really good reason why not, in terms of grades being reduced for those reasons. There are 2 quizzes that happen in the beginning half of the term, just on the material covered in the class, the labs, and the assignments, as well as assignments, P-sets, lab stuff. Everything should be turned on via Stellar, unless it's something that can't physically be turned in electronically. Last year I had issues with stuff getting lost, and so this is my hope that nothing will get lost. So just make sure it makes it on Stellar, and hopefully Stellar won't disappoint. Are there any grad students? Okay, so if you want G level credit as opposed to undergrad credit, you need to sign up for a different subject number. So you can talk to me afterwards and just send me an email telling me that you're signing up for the grad class, because if I don't know that, I will not be able to tell the person who actually writes in your grade the right grade, and then you'll get an F without me even knowing that, and that would stink. So yeah, most of the readings are going to be handed out online, basically. So while there is a required text, which I think is a great text, of Paul Polak's Out of Poverty, it's totally something that you could borrow from a friend or grab from the library, because it's not like we're referring to it every week and you need to have it heavily highlighted and in your grasp at all times like you would a math textbook or something. But Paul's a good guy, so if you can afford the book, which is like $14, it's worth supporting him. So the structure of the class is, the first half of the class is lecture and lab heavy. It's sort of like a normal class where, like today, I'll be doing talking, probably not as much talking as I've done today ever again. We try to do a lot of hands-on exercises in class too, but there will be a decent bit of talking. And then the labs, which are very hands-on and run by Amit, where we build a biodigester, we build a solar panel out of solar cells, we build a little tiny wind turbine, you make charcoal, you do all stuff that's very hands-on, relevant to what we might be doing in Nicaragua. And then subsequently over spring break, most people travel to Nicaragua with the class, which is a really fabulous experience that's extracurricular. It's not a requirement of the class to go to Nicaragua, but it does add a lot to your experience. Actually working with real people rather than them just being hypothetical is a pretty valuable addition. And then after the trip, you come back and it's very much a design class where you're working on a project identified in Nicaragua, or really identified beforehand, that you learn more about in Nicaragua, and then you work on it for the last half of the class. The lab and lectures basically disappear, and it's all just work time with a little bit of lecture content to help you with the design process. So that part is pretty intensive. And then you do final presentations. We hand off the projects to Nicaragua one way or another, and the class is over. So that's how it's split up. What else? One thing to know is for people who are going to Nicaragua, it's really helpful to speak a bit of Spanish. And so one of the more random homework assignments is to at least listen to a couple podcasts per week of a Spanish podcast, like Spanish learning podcast, so that you can at least say hi and thank you and things like that. If you happen to speak Spanish already, bonus. But if you and you know, if you're fluent, no need to practice. But if you're not, it's nice to get a little practice. If you've taken like Spanish 2 or something in high school, it's nice to practice a little because that stuff tends to come back quickly if you practice and not if you don't. And I will start speaking a little bit of Spanglish. I have taken all of Spanish 1 at MIT, so I am not your Spanish expert, but I have spent, by now, over the course of different weeks, probably a couple of months in Nicaragua, so my Spanish is a bit better when I talk about technical things that I know about in Spanish than just general conversation. But yeah, so I'm not expecting you to be a Spanish expert through a technical class, because that would be ludicrous, and I'm not myself, but it is helpful to know a little bit of the language. Finally, just one thing is, one of the things you picked up is a muddy card, which you may or may not have encountered at MIT, and it's just a way to give feedback to me about what you understood, what you valued about the class, what you didn't understand, hated, completely anonymously, and it allows me to improve my teaching in the class. I am finishing up my PhD. I aspire to be a professor, so I really want to improve and appreciate your help in that, and appreciate constructive criticism. It doesn't have to be that constructive. It's useful for me. And it's anonymous, so you can be blunt. Or if there's something you loved, it's great to hear that too, just to know what to keep in the class. But I really appreciate you taking the time to do that. And then we also have similar stuff with the readings, just getting feedback online on the forums. Do you guys have any questions about the syllabus and what I just went over? Okay, cool. So in order to get into the class, because it is a class where you get to travel to Nicaragua, there's a big commitment in terms of we're working with real people in Nicaragua, and so we want to make sure that you're here to really work and not just to fill out your class requirements or whatever. We do have kind of a strict what you have to do. So one is a student profile where you just tell me about yourself. That's online, linked to on Stellar. And the other thing is a DIY lantern. So I'm going to give you all an LED and a 9-volt battery. You can pick up a resistor, and you need to figure out what resistor you need from the Edgerton Center. And this is all online too, but it's room 409. This is the combo. The resistors are on your right, so you need to figure out what your resistor is. I would recommend checking that the resistor you pull out of the drawer is actually the right resistor by looking up the resistor code and doing the work, because the Edgerton Center is a student lab, and so resistors tend to get mixed up. And if you pick a wildly wrong resistor, you will blow your LED or your device won't work at all. But on the flip side, resistor, the V equals IR equation in terms of how flexible an LED is relatively flexible. So if you can't find the exact resistor you've calculated the value for, go up or down 10 or 15% and you'll be fine. So anyway, so you're trying to build a lantern out of found materials, that resistor, the 9-volt battery, and the LED. And what I care about is, does it function? So does it turn on? Is it possible to turn it on and off? And can I figure out that switch in a reasonable amount of time? Aesthetics, does it look decent? Did you use materials creatively? So if you found a lantern at EMS or REI tonight and bought it and just swapped out the internals with this, that would not be a very creative use of found materials. So I'm hoping that you actually find stuff that's recycled rather, and then maximizing light. Is it actually useful as a lantern? So those are the criteria. And you can bring the lantern back to just the room down the hall is E34 211, and just place it on a desk with a piece of paper that has your name, a really quick sketch of the lantern so that we remember what it is when we give the lanterns back to you, and just a really fast explanation of how you size the resistor so we know that you understand that aspect of what we just went over. Are there any questions about this assignment?
What do you mean by materials? I didn't quite understand. Like,
Found materials?
are we just supposed to have like an LED or like construct something around the LED?
Yeah, so
The
you...
LED is like this big, right?
Mm-hmm.
So how your lanterns like this big? So you make like a paper covering or something?
That would be one way to do it. Yeah.
Are there going to be materials available in the lab, or?
So I'm sure you can find some materials downstairs. Downstairs there's a not in the Edgerton lab. The Edgerton lab you can just get resistors. Downstairs, and we actually intentionally tried to make this class a little short so there's time to help you start this project. So downstairs in there's the D-Lab shop, and there's some scrap materials in there that you can scrounge, or the recycling bins in dorms, at least back when I was a student here, undergrad student, were pretty full of wild things that might be useful. And MIT trash cans are amazing in terms of what's there. Just walking the halls where people have piles of stuff that they're throwing out. There's all sorts of stuff that you can grab. But yeah, the idea is to just use found materials, because when you're in the field, you're often just looking around in the trash heaps. And yes, the trash heaps in developing countries and some regions are really more useful than in other places than here for getting trash. People are also more creative, so they tend to use up all their trash, so there's not much left. So it's a trade-off. So in some respects, we have worse trash piles, and in other respects, we have better trash piles. But the idea is to make a lantern with trash and the components that I give you. Do you have any other questions about it? Yeah.
Can we use other electronic components like a switch, or do we just get creative with those as well?
So you have a trade-off, a design trade-off here. I want it to function, which might push you toward using a switch, and I want you to be creative, which might push you toward using something that isn't a traditional switch. And that's really your call. And so if you decide that the switch is the right call because you're going to value functionality, maybe you do something else that's a creative use of materials in a different realm, so that you try to meet all things. But in every design process, there's going to be direct conflicts. And I need it to be super lightweight, and I need it to have a huge battery pack. That's a classic design conflict, and I'm trying to reproduce that here.
You can just pick up a switch from the project lab?
No.
No. So you can only pick up
A resistor. So I will hand you out an LED and a 9-volt battery right now. Actually, if you want to do that. And then you can get the resistor from the Edgerton Center, and everything else is found materials. So the homework for this week is this reading, which is online. Write a reaction piece. The instructions for how to write a reaction piece, which it's like a paragraph, it's not onerous, is on the Stellar forum. And then there's a problem set with 2 problems on it that's also on Stellar.
Do next week?
Yeah.
So once we find out that we're in the class.
Right. So I will let you know if you're in the class by midnight tomorrow. So that gives you plenty of time to do the homework after you find out. So, but conveniently, fewer people showed up than said they were going to show up. So the ratio of people getting in should be pretty good. So yeah. So if you guys can take 5 minutes to do the muddy cards, I would really appreciate it. And then you can leave. You can head downstairs and look for found materials. You can talk to me right now, whatever you want.